Welcome to Lecture 1.1, Vector Spaces. We'll start with a definition that will motivate the main ideas of this section. A real-valued function f is said to be linear if the following relation holds. If f of ax plus by equals a f of x plus b f of y. In other words, in plain English, this just says that you can break apart sums and pull out constants. And in fact, there's an equivalent definition, which instead of having one condition like above, has two conditions, and those are break apart sums, f of x plus y equals f of x plus f of y, and pull out constants means that f of ax equals a f of x. And I'm not writing it here, but I'm saying, obviously, in these definitions, this or these have to hold for all x and y inputs and all constants a. And lastly, when I say real-valued function, I mean a function whose output is a real number. So I'm not specifying what the input is. So f might be a function from r to r. That's how we say this. You input a real number and you output a real number. You've seen things like that, like f of x equals 3x. That's linear. When that's not linear is sine of x. Or f could be a function from, say, r2 to r. And that just means that the input is a two-dimensional vector. We usually write it as f of xy, and 3x plus 4y. There's an example of a linear function from r2 to r. Or a nonlinear example is e to the x sine of y. Now, these are all real-valued functions because their outputs are real numbers. Many common structures and operations have this linear property. For example, derivatives. If you take the derivative d dx of au plus bv, then that is equal to a times du dx plus b times dv dx. Integrals. The integral of a linear combination of functions, au plus bv, is just a times the integral of u plus b times the integral of v. Matrices and vectors have this property. A matrix M times ax plus by is equal to a times mx plus b times my. Now, some of you already know this, but the reason why is because a matrix M, if M is m by n, then that secretly represents a linear function from Rn to Rm. We'll talk about this in a later lecture. Some of you have no doubt seen this already. And then the inputs being n-dimensional vectors, that means that x and y are length n vectors, and then the outputs, this here, is an m-dimensional vector. Laplace transforms are linear. The Laplace transform of AF plus BG, you may remember, you can just break those apart into sums. A times LF plus B times LG. Solutions of certain differential equations have this linearity property. And here's an example. So here's an ODE. Y double prime plus k squared y equals 0. This is a linear ODE, which we'll talk more about later. But what that means is that if you have two solutions, y1 and y2, that solve this ODE, then any linear combination of those, c1y1 plus c2y2, is a solution as well. So this particular example, I've presented things a little bit differently than the ones above. I mean, here I gave you two solutions, y1 and y2, and I concluded that a linear combination is a solution. But convince yourself, take a moment, to see why this really is the same property as what we have above in Laplace transforms, matrices, integrals, and derivatives, namely this linearity property, breaking apart sums and pulling out constants. We encounter this type of linear structure all the time in mathematics without even realizing it. You've done it a lot already in your first couple years of college mathematics. A beginning linear algebra class usually focuses on systems of equations in matrix algebra. As I said above, an m by n matrix encodes a linear map from Rn to Rm, and elements in these sets are called vectors. However, most introductory linear algebra courses don't focus on this. They're more concerned with computational aspects, like how do you solve a system of equations, how do you find the null space. But behind the scenes is the important theory that these matrices represent linear maps. And we'll talk more about that in this class shortly. But even this fact that a matrix secretly is a linear map from n-dimensional space to m-dimensional space, even that is a special case of the bigger picture, which I've shown you above, something that holds for derivatives and integrals and ODEs. We'll begin this course by peeking at this structure because it underlies nearly every aspect of the mathematics in this class. And the more you can understand and see the big picture, the more natural, not just the math in this class, but everything going forward will be for you as well. A vector space is one of the most fundamental objects in linear algebra. Here's a definition. A vector space consists of two things. First, a set V, think of these as vectors, and a set F, think of these of scalars. They're usually either the real numbers or the complex numbers. And then there's two properties that have to hold, and they're very natural. V is closed under addition. What that means is if you take any two vectors in your set and you add them together, you get another vector. Also, V is closed under scalar multiplication. That means that if you take any vector and any scalar and you multiply them, then you get another vector. From this simple definition, we can deduce some easy consequences. First of all, the zero vector is contained in V. Why? That's because the set of scalars has to contain 0, and if we take any vector and multiply it by 0, we get the zero vector. Secondly, for any vector in our space, its negative must be in our space as well. For here, we can just take the scalar, which is -1, and take V times -1, and we get negative V. Now, several other comments. I've said that our set of scalars is a set, either the real numbers or the complex numbers. Technically, it's something called a field, which is a very nice mathematical object of numbers that you could multiply, subtract, add, and divide, except you can't divide by 0. So without giving you a definition of that, it's not really that relevant for this course. Examples of fields are the rational numbers, the real numbers and complex numbers. There Z2, or some people call it F2. This is the binary field. It contains 0 and 1. You can do the same thing. Take CP for any prime number, and you get the numbers 0 up to p minus 1. And addition and multiplication is done modulo p. And then there's many, many other fields that are a little bit stranger than these. But in this class, the only ones that we will consider will be the real numbers or the complex numbers. If our field are the real numbers, then we say that V is a real vector space, an R vector space, or a vector space over R. A complex vector space is defined similarly, and then we say it's a C vector space or a vector space over C, or over the complex numbers. A blanket assumption in this class is unless specified otherwise, you can always assume that by default our field is the set of real numbers. There will be times when we do want to specify that it's the complex numbers, but it usually should be clear from the context. And one more remark that I didn't fit on this slide is in this definition, we can add any two vectors, and we can get the negative of any vector, so we can subtract any two vectors, and we can multiply vectors by scalars, but we are not allowed to multiply vectors together. Now, there are special cases of vector spaces when you can multiply vectors. There's a natural definition, but that is not always the case. So when you see vector space, think addition, subtraction, and scalar multiplication, but you cannot necessarily multiply two vectors together. Let's do some examples of vector spaces. The most basic one that you've seen before is n-dimensional Euclidean space. We usually call it Rn. It just consists of n-tuples of real numbers. Now, sometimes we write these n-tuples vertically, like x1, x2, all the way up to xn. It doesn't make a difference. This n-tuple and this n-tuple are the same. This is often more convenient if we're trying to write it in a sentence, like in a book, like here, because it just doesn't take up all that extra vertical space. So why is this a vector space? Let's check. It's closed under addition because if we have any two vectors, x1 up to xn and y1 up to yn, and we add them up, we get another vector. And x1 plus y1 dot 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 xn plus yn. That is clearly an element of Rn. So this space is closed under addition. Why is it closed under scalar multiplication? We'll take a scalar, c, and multiply it by a vector, and you can pull that scalar inside, and you clearly get another vector. Next, cn. That's the same thing as Rn, but the entries are now complex numbers. I'm not going to check the same two properties, but it should be pretty clear that this set is closed under addition and scalar multiplication. And here should say that our set of scalars is usually assumed to be the complex numbers, not the real numbers. Third example, I'm going to call this Rn of x, or Rn bracket x, and it's the set of polynomials of degree less than or equal to n. So convince yourself that if you take two polynomials of degree n or less, and you add them together, you clearly get another such polynomial. Or if you take a polynomial and you multiply by a real number, you still get another polynomial of degree less than or equal to n. So this is the first example that we've seen where the space of so-called vectors don't look like what we normally think of as vectors, which are n-tuples of complex or real numbers. Here, our vectors, in quotes, are polynomials. But there's nothing wrong with that. It satisfies the two properties of being a vector space. Here's another example. Let's drop the degree less than or equal to n condition. Now let's look at polynomials of arbitrary degree. That's a vector space as well. We'll see shortly that this is an infinite dimensional vector space. Now, we haven't defined what dimension means, but hopefully that makes sense that this is infinite dimensional because you can have polynomials of arbitrary degree. Clearly, these things are closed under addition and under scalar multiplication. The next example regarding polynomials is the space of power series. Think of these as polynomials that do not necessarily end. They can be infinite. Now, don't worry about convergence here. For normal calculus, if you have a power series, you have to worry about when it converges and when it doesn't. For example, 1 plus x squared plus x cubed. This only converges if x is from -1 to 1. But we don't care about that in this set. We're looking at the set of all formal power series. And so this is a formal power series. And these things are clearly closed under addition and scalar multiplication. You take two power series, you add them up, you get another one. You multiply one by a scalar, you get another one as well. So now we're going to go into another class of vector spaces, those of functions. So the first ones were your standard classic vector spaces of n-tuples. Now these are spaces of polynomials, and these are spaces of functions. I guess polynomials are functions, but here I mean things like continuous functions. So C1 of R, so R means that these are real valued functions, and the 1 means that they are once differentiable and that derivative is continuous as well. Similarly, there's the space C infinity of R. This is the set of infinitely differentiable functions, and all of those derivatives have to be continuous. Sometimes functions in here are said to be smooth. And usually we don't write the R, we just say C infinity, and we assume, unless otherwise specified, that the functions are real valued. Now these two are different spaces. Every infinitely differentiable function is also once differentiable, but it's actually really hard to find examples of functions that are differentiable once but not twice, or differentiable 5 times but not 6 times. So in practice, most of the functions that we deal with on an everyday basis, things like polynomials, exponential functions, sines, cosines, things like that, those actually are infinitely differentiable functions. So usually we will deal with C infinity rather than C1 or CK, which you can imagine how that's defined. And again, these examples 3, 4, and 5, these are examples where your vector spaces are functions, and so are these. These functions, however, are not polynomials. They are things like e to the x and sine. And it should make sense why something like this, C infinity, is a vector space. Let's take two functions, f of x, say e to the 2x minus 3, and g of x equals sine of, cosine of 4x, 4/3 x. If you take these functions, which are both infinitely differentiable, and you add them up, you get another function in C infinity. If you take either of these and you multiply by a scalar, you get another function in C infinity. So here, these really don't look like vectors, but since this is a vector space, we are abstracting the notion of vectors from up here. These things are vectors, and the real numbers are scalars. Finally, our last example is the space of piecewise continuous 2 pi periodic functions, and that just means that f of x equals f of x plus 2 pi. So that doesn't mean that the period is equal to 2 pi. It means that if the function is non-zero, then the period is 2 pi over n. So the period divides 2 pi. For example, what's an example of this function? Sine of x. That's easy. What's another example? How about sine of 2x? So notice that this property just means that if you take the value of some x naught and compare that to x naught plus 2 pi, then the corresponding outputs are the same. So that means the function repeats every 2 pi. But that doesn't necessarily mean that it repeats exactly every 2 pi. Like here it also repeats every pi. You could have done the same thing. This is down here, this is x naught plus pi. So this function has period pi, this is period 2 pi, but they are both 2 pi periodic. And if you add these things together, you're still going to preserve this condition, that it's 2 pi periodic. And clearly, if you multiply these by a scalar, then the function is 2 pi periodic as well, even if that scalar is 0, because the 0 function is clearly 2 pi periodic. It obviously satisfies this condition. To solidify the concept of a vector space, it helps to see some non-examples. The first one is if you look at the polynomials with degree exactly n. Those are not closed under addition, because here's two examples, x to the n plus 1 and 2 minus x to the n, where if you add them up, you get 3. This is a degree 0 polynomial. This also is not closed under scalar multiplication, because if you multiply a degree n polynomial by 0, you don't get a degree n polynomial. Secondly, the upper half plane in R2. So this looks like all vectors that are north of the x-axis. Now, I haven't specified whether this should include the x-axis or not. It doesn't really matter. But what you should understand is that this space is not a vector space. Well, why, first of all? If you take any two vectors in the upper half plane and you add them up, you get another vector in the upper half plane. So this set actually is closed under addition. But it's not closed under scalar multiplication, because if you take any vector v and you multiply by its negative, then you get, this is negative v, you get something that's not in the upper half plane anymore. So this is not a vector space. Finally, if you take any line or plane that is not through the origin, meaning it does not contain the zero vector, then that is not a vector space. Why? Well, it's not closed under scalar multiplication. If you take any vector v multiplied by 0, you get 0, which is, by assumption, not on your line or your plane. It's also not closed under addition either. That's not quite as obvious, but let's do an example and you'll see. So here's a line that's not through the origin, and let's just take two vectors on that line. Let's add them up, and it should be pretty clear that what you get is not on that line. So this is u, and this is v, and this is u plus v. If v is a vector space over a field F, and then a subspace of v is simply any subset of vectors that is also a vector space in its own right. Has to be over the same field F as well. And we'll sometimes use this less than or equal to symbol to denote that W is a subspace of V. Every vector space has two very trivial subspaces. There's the space itself. V is clearly a subset of V and also a vector space. And then there's the subset containing just the zero vector. That also is clearly a subset, and it's a vector space because it's closed under addition. You add 0 to itself and you get 0. And it's closed under scalar multiplication. You multiply the zero vector by a scalar and you still get the zero vector. Here's a less trivial example. Let's take R3 and consider the set of vectors where the z-coordinate is 0. Now we say that that's not equal to R2, but we say it's isomorphic to R2. We won't define that, but hopefully it's clear what we mean by this, that this looks like R2. It's got the same structure of it. So here's V, which is R3, and geometrically, W is just the xy plane. So it's the set of vectors whose z-coordinate is 0, and that it's clearly a vector space, because if you take any two vectors in here and you add them up, you get something else in this set. And you take anything like this and you multiply by a scalar, you get something in that set as well. So it's geometrically obvious, but if you want to prove it rigorously, you have to say that take x1, y1, and 0, and add it to x2, y2, and 0, and you get something that is x1 plus x2, y1 plus y2, and 0, and that is in the set W. So this symbol means in. So the sum of these two vectors lies in W. And also, if you take x, y, 0, and you multiply by c, you get cx, cy, 0, and that lies in W as well. Here's another simple example. The space of all polynomials of degree at most n is a proper subset of the space of all polynomials of any degree, which is a proper subset of the space of all power series. And that is if you allow a power series that eventually ends in 0 to be thought of as a polynomial. So for example, 1 plus x plus 3x squared plus 0x cubed plus 0x to the fourth. So something like this we can think of as a polynomial. So every polynomial can be written as a power series that eventually just ends in zeros. So these are easy containments as subsets, but since these are all also vector spaces, then this is a containment of subspaces as well. For example, the space of polynomials of degree at most n is a subspace of both the space of polynomials and the space of power series. Also, the space of polynomials is a subspace of the space of power series. And just like subsets, subspaces are transitive. So if x is a subspace of y, which is a subspace of z, then x is a subspace of z. And that follows straight from the definition. C infinity is a subspace of C1. I've said this before. This is clearly a subset of C1 because every infinitely differentiable function is once differentiable, and because this is a vector space, it's therefore a subspace. More generally, we can define Ck of R to be the space of k differentiable functions, and we want those derivatives to all be continuous as well. And if we do that, we have this chain of containments where C1 contains C2, contains C3, etc., and then all of these things contain C infinity. As I said earlier, it's really hard to come up with an explicit example of something that is, say, in C3, but not in C4. So usually we just deal with C infinity, but be aware that all of these do exist, and they are distinct. And this is not just a chain of subsets, it's a chain of subspaces. Each of these is a subspace of everything to its left. Finally, I want to leave you with a remark that subspaces in n-dimensional space, this is the vector space that we are all the most familiar with, these look like, geometrically, hyperplanes. By that I mean lines, planes, or higher dimensional planes that go through the origin. That's the key point. They have to contain the zero vector. Let's do some non-examples. The unit circle in R2, that is not a vector space. Well, it does not look like a hyperplane, a line, a plane, or some higher dimensional analog. And also, if you take any two vectors on the unit circle and you add them up, you get something that's not on the unit circle. This is clearly not closed under addition. It's clearly not closed under scalar multiplication. You take a vector on the unit circle, you multiply it by 2 or by 0, and you no longer stay on the unit circle. Polynomials of degree n, that is not a subspace. As we've said before, it's not closed under addition or under scalar multiplication. The upper half plane, we established that that is not a vector space, so it cannot be a subspace. The line y equals 2x plus 3, that looks like a line or a plane, but it's not through the origin. It is not a vector space, therefore cannot be a subspace. The plane of height 1 in three-dimensional space, or in R3. So that looks like a plane, but it's not through the origin. So it does not contain the zero vector, and it is not a vector space, and hence not a subspace of anything. Finally, we'll finish with a more subtle example. That is the set of piecewise continuous functions with period exactly 2 pi. I claim that is not a vector space, and hence not a subspace of the space of all 2 pi periodic functions. Recall that this was a set of all functions that satisfied f of x equals f of x plus 2 pi. Now before I explain why this is not a vector space, let me say a few words about a subtlety that I didn't mention earlier, but maybe you should have, namely why this word piecewise is here. It's just because there are a lot of functions that come up in engineering. You may remember your ODEs class. You saw things like square waves or step functions. So something like this, square wave, is not a continuous function, but we can do things like let that be the forcing term of an ODE and solve that ODE. So here's another one, a sawtooth wave. And so because these things come up in the study of Fourier series and ODEs, we want to include them in our space of 2π periodic functions, and therefore we just add the word piecewise. So we relax that definition. And we'll see more about this later when we study Fourier series as to why this is very natural. So why is this not a vector space? Well, let's take any of these functions, say f of x, and let's multiply by 0, and we get the 0 function, and that is not a function with period exactly 2π. It satisfies this property, but it's not a function. It doesn't have a finite period. Well, so that's not the only reason why this is not a vector space. Let's do a more subtle example. Let me take f of x equals sine of x plus sine of 2x. I hope that you'll agree with me that this function, it's not easy to draw, but this, well, so sine of x has period 2π and sine of 2x has period π. And if you add them together, you're going to have something of period 2π, not of period π. But let's define g of x to be negative sine of x. That also has period exactly 2π. But if you take f of x plus g of x, you get sine of 2x, and now both of these have period 2π, and this has period π. So that's another reason why this set is a subset, but it's not a subspace. Finally, we'll conclude with a summary, how to determine whether W is a subspace of V. So let's suppose that you're given a collection of vectors. They could be n-tuples, they could be polynomials, they could be functions. But some collection W that is contained in a vector space V, you need to ask the following two questions. Is it closed under addition? If I take any two of these vectors and I add them together, do I stay in that set W? And finally, is it closed under scalar multiplication? If I take any vector in W and I multiply it by a number, don't forget to try negative numbers and 0, do I remain in that set as well? If and only if both of these conditions hold, then W is a vector space and hence a subspace of V.